Hi everyone. So today we're going to be finishing up with our notes on Unit 3, Lesson 5. So we're picking up on page 20 here, and we're starting with this density of a gas. Remember, we've been talking about our gas laws. Okay, so this is a new equation that we're learning this year, and it's going to show me that a density of a gas at any given temperature and pressure is directly proportional to its molar mass. So we have two ways that we can look at this formula. We have that our D, which is density in grams over liters, is equal to P, which is pressure, times this capital M, which is the molar mass in grams per mole, divided by R, which is our gas law constant, times T, which is our temperature in Kelvin. Or we can remember that our molar mass, which is M, is equal to density times the gas law constant times temperature over pressure. I personally memorize the M equals dRT over P equation. For me, that's just easier to memorize, but you can pick which equation you want to memorize and then extrapolate or use your algebra skills from the equation that you have memorized to get to the other one. These equations, unfortunately, are not on the reference table, so you definitely should have at least one of them memorized, but let's apply them in this first practice question. So this first practice question says calculate the density of sulfur dioxide gas at 35 degrees Celsius and 1270 torr. So I'm going to be using my formula, this D equals PM over RT. Okay, so I'm solving for my density here. Okay, I know my pressure. Okay, so I'm solving for density. I know pressure is 1270 torr. I know my molar mass. Well, this is sulfur dioxide, which means it's SO2. So if I go to my reference table and add up these masses to get my molar mass, should come out to 64.06 grams per mole. And I'm confident that you guys don't need me to walk you through how to calculate the GFM here. Okay, over my gas law constant, which I'm going to use 62.36 in this example because we're dealing with torr. Okay, so torr means that I'll be using the 62.36. And then my temperature here, okay, I've got this 35 degrees Celsius, but I know that I need this in Kelvin, so I add 273 to this temperature, and that would get me this number of 308 here. So I plug all of this in, I solve for my density, and I answer with sig figs and a unit here. Okay, so my answer should be 4.24, and then my unit is grams per liter. Okay, so let's look at another question like this in practice number 2. So in practice number 2, it says that an evacuated 1 liter flask weighs 346.580 grams when filled with a dry gaseous element at 25 degrees Celsius and 725 torr. The flask weighs 349.326 grams. Use these experimental data to determine the identity of the element. So if we're determining the identity of the element here, we're really looking for that molar mass. If I look at my density equation, really the only thing that will identify my element is going to be that molar mass here. Okay, so that's what I'm solving for. So I'm going to use that density equals PM over RT equation again. Okay, I'm going to be able to figure out my density here. How I'm going to figure out my density is I'm going to look at this mass of my evacuated flask and my mass of my substance with the flask, and I'm going to subtract those to get the mass of just my substance. Then I know that that gas is occupying this 1 liter because it's a 1 liter flask, so I can put my grams over liters to determine my density here. So to get the mass of this substance, I take the mass of the flask with the substance, which was this 349.326 grams, and I subtract from it the mass of the empty flask, which was 346.58 grams, and that's going to give me a mass of 2.746 grams. And I know that this is the grams in 1 liter, so I divide that by 1 liter, and I get a density of 2.746 grams per liter. So now that I have this, I'm going back to my density equals PM over RT equation. I could also write this as molar mass equals dRT over P. Okay, so my density I just solved for was this 2.746. Solving for molar mass again. My R here, I'm going to be using that 62.36 again because my pressure is in torr. Okay, my T, my temperature, tells me it's 25 degrees Celsius. Again, I need that in Kelvin. So I add 273. That gets me to 298 Kelvin. And then on the bottom here, my pressure was 725 torr. So I plug all of those numbers into my calculator, and I round this to have sig figs in a unit, and I get about 72 grams per mole here. Then to determine the identity of my element, I'm going to go to my reference table, and I'm going to look at my masses of my individual elements, and I'm going to find which one is closest to this mass. And what I can see is that I'm closest to the mass of Ga here, of gallium. All right, so that is my density and molar mass equations. And we can also look at gases in terms of their partial pressures here. So the partial pressure of a gas is the pressure exerted by an individual gas in a mixture of gases. So if I have a mixture of gases in the air, for example, in the air I have got oxygen, I've got carbon dioxide, I've got water vapor, I can measure the partial pressure of each of those gases individually. All of those partial pressures in that mixture will add up to give me the total pressure of the mixture. And that's Dalton's law of partial pressure, which says that the total pressure of a mixture of gases equals the sum of the pressures that each gas would exert individually, which corresponds to their partial pressures. So we say that the P total is equal to the P of the first gas plus the P of the second gas plus the pressure of the third gas for however many gases are in the mixture. Each gas in the mixture behaves independently from one another in the mixture, and the pressure exerted by each can be calculated using the ideal gas equation for that gas individually. So again, if I have this mixture of air, and we're talking about oxygen and carbon dioxide and water vapor, I could do an individual gas law equation specifically using the moles of that gas to figure out the pressure that that individual gas is exerting in my mixture. I can also calculate this using a mole fraction. If I know the number of moles of each gas in a mixture, I can determine this mole fraction, which I signify with this capital X here. The subscript on that X is going to be the identity of the gas that I'm looking at. So it's going to be the chemical formula of that gas that I'm looking at. And the mole fraction is a ratio of the number of moles of the substance that you are studying over the total number of moles of the gas in the compound. That's how I calculate the mole fraction for each of these substances. So if I know the total pressure of the mixture, and I know the moles of my individual pieces in the mixture and my total moles in the mixture, I can calculate the partial pressure of each gas in the mixture using this formula. The partial pressure of the gas that I'm studying, or gas A, is equal to the mole fraction of gas A times the total pressure. So let's look at this in an application here. I see in this practice question number 1 that a mixture of gases contains 4.46 moles of neon, 0.74 moles of argon, and 2.15 moles of xenon. I want to calculate the partial pressure of the gases if the total pressure is 2 atmospheres at a certain temperature. So what I want to do, I'm going to be doing an individual calculation for each of these. I need to calculate the mole fraction for each of my substances in the mixture. So first I need to know the total moles of substances in the mixture. I'm going to find that total moles, which I'm going to call X total. So that's going to be my total number of moles by adding together all of the moles in the problem. So I'll take 4.46 plus 0.74 plus 2.15. And that's going to show me that I have a total of 7.3 moles in the mixture. Then I can calculate the mole fraction of each gas individually. So if I want to calculate the mole fraction of Ne, I'd write this as X and then subscript Ne, and it's going to be equal to the moles of Ne, which are 4.46, over the total moles in the mixture, which is 7.35. So that's going to give me this mole fraction of 0.607. To then calculate the partial pressure of neon, which is what the question is asking me for, that partial pressure of neon is going to be equal to the mole fraction of neon times the total pressure, which they give me in the problem. So that partial pressure of neon is going to be equal to this 0.607 times my total pressure of 2 atmospheres. And that's going to give me 1.21 atmospheres here. So that's the partial pressure of just the neon gas. And I can do this for all of my gases in the mixture. I can calculate my mole fraction of argon by taking the moles of argon, which is 0.74, over my total moles in the mixture. And that's going to give me a mole fraction for neon of 0.1007. Then I can calculate the partial pressure of argon by taking that mole fraction, which is that 0.1007, and multiplying it by the total pressure. That's going to give me a partial pressure of 0.201 atmospheres for argon. Then I can do the same thing for the xenon. So my X of Xe, again, I'm taking the moles of Xe, which was 2.15, over the total moles in the mixture, which was 7.35. That's going to give me a mole fraction of 0.2925. Then to find the partial pressure of that xenon, I'm going to take my mole fraction, which was 0.2925, times the total pressure, which is 2, and that's going to give me a partial pressure of 0.585. I can also look at a mixture of gases collected over water using a setup looking very similar to this below. We might be able to do this in the lab this year, although I'm not 100% sure yet. We'll see if we are able to do it. But if I'm looking here, okay, my total pressure of my mixture that I have, what I'm doing here, I'm taking a substance and I'm bubbling some gas through this tube that I have here, and I'm bubbling it through the water. This gaseous water vapor plus whatever gas I'm studying is going to rise up into this test tube that I have right here. And I'll be able to measure the total pressure in that test tube, and I know that that total pressure is going to be equal to the partial pressure of the gas that I'm studying plus the partial pressure of the water vapor that I created. So if the gas that I was studying was O2 here, my total pressure would be that pressure of O2 plus the pressure of the water vapor in that tube. And I can use this relationship to try to calculate information about that unknown gas that I'm studying. So for example, here in this practice problem, practice number 1 says that oxygen gas is generated by the decomposition of potassium chloride collected over water. The volume of oxygen collected at 24 degrees Celsius and atmospheric pressure of 762 millimeters of mercury is 128 milliliters. Calculate the mass in grams of oxygen gas obtained, and it tells me that the pressure of water vapor at 24 degrees Celsius is 22.38 milligrams of mercury. So what I'm looking at here, that atmospheric pressure is going to equal my total pressure in that test tube. So if we scroll back up to this picture, this total pressure should be equal to the atmospheric pressure here. And I know within this test tube, I've got both the water vapor and whatever gas I'm trying to study. So specifically here, I'm trying to study that oxygen. So if I know that my total pressure is the 762 millimeters of mercury, okay, again, I know that that's my total pressure here, the 762 millimeters of mercury. And I'm looking to isolate just the pressure for my oxygen. I know that this 762 is going to be equal to my pressure caused by oxygen plus the pressure of the water vapor here. And I know what the pressure caused by the water vapor is because it tells me right here. So to solve for my pressure of my oxygen, I'm going to take that 762, which was the total pressure, and subtract from it the pressure of the water vapor, which is this 22.38. So that'll give me my partial pressure of oxygen as being 696 millimeters of mercury. Remember, millimeters of mercury is another way of saying torr. And so then what I'm going to do, now I can do a little bit of ideal gas law equation here. Sorry, I lost my train of thought there for a second, but I can do my ideal gas law equation to figure out my moles of oxygen gas that I obtained from this. So I'm going to use my PV equals nRT equation. Oops, sorry, my pen is dragging. I'm not sure why. Okay, and I know my pressure caused by my O2 gas was this 696 millimeters of mercury. That's what I just calculated here. And I'm doing this ideal gas law equation just for my oxygen because they're only asking me about the mass of oxygen produced. They don't want to know about the water vapor. So I just want my partial pressure of oxygen in this problem. Okay, I know that the volume of oxygen collected was this 128 milliliters. Now in this problem here, I don't want milliliters, so I should convert this to liters, which would be 0.128 liters. And how I know that I don't want milliliters is if we look back at the units for our gas law constant, our R value, the volume unit in that constant is liters. So anytime I'm plugging volume into my gas law equation, I do want it to be in liters. I'm solving for my N, that number of moles. My gas law constant that I'm using here is 62.36. Again, that's what we use for torr or millimeters of mercury. Then my temperature, it tells me it's 24 degrees Celsius, but I do need that in Kelvin because we know that these gas law equations always require the temperature in Kelvin. So that would be 297 Kelvin. So I do a little bit of algebra. I solve for my N, and it should come out to 0.005114. Now, I'm not rounding this to have sig figs just yet because this is not the end of the problem. Okay, they didn't ask me for the moles of oxygen gas. They asked me to calculate the mass in grams of oxygen gas. So my last step here is to do a mole conversion, and I know that 1 mole of oxygen gas is 32 grams of oxygen. So I take this number and multiply it by 32, round my final answer to have sig figs, and I should end up with 0.164 grams of O2. Okay, so I'd like you guys to take a second and try this question here, this practice number 2. Okay, so we're going to be doing a very similar process here where I've got my total pressure and I know the vapor pressure of my water, so I'm going to be able to subtract that out from my total pressure to get the partial pressure of just my hydrogen gas. So the partial pressure of my hydrogen gas is going to be equal to that total pressure minus the pressure caused by the water vapor. Okay, and that's going to go, sorry about that. That's going to give me this partial pressure for hydrogen gas, and that's going to be equal to 696 torr. Okay, so now that I have my partial pressure of this hydrogen gas, I'm again going to plug it into my PV. And PV equals nRT equation, that ideal gas law equation. I'm not sure why my pen is dragging. I'm sorry about that. Okay, so I know I'm looking at this just for hydrogen. So my pressure is 696. My volume, it tells me, is this 255 milliliters, but again, I want 0.255 liters. I'm solving for my X, which is my number of moles. Gas law constant is 62.36. Then the temperature is 24 degrees Celsius, which again, I'm going to add 273, and I should get 297. So my X here, when I solve for my number of moles, would be 0.00958 moles of hydrogen. Okay, so that's the first part of my answer here, the how many moles of hydrogen were produced. Second part is how many grams of zinc reacted. So for this, I'm going to need a balanced chemical equation. So it tells me that this hydrogen is produced by the action of sulfuric acid on zinc metal, which means I'm reacting together zinc metal and sulfuric acid, which is H2SO4. This is going to be a single replacement reaction, which means that zinc is going to replace hydrogen in the compound. So I'll end up with ZnSO4 plus this free hydrogen gas. Now I have to balance this equation. So if I'm looking at this, it should be balanced for us already, which is nice. It's a 1-to-1 ratio. So then I'm going to take the moles of my hydrogen gas that I just solved for, this 0.00958 moles of hydrogen. Again, I want to know how many moles of zinc reacted. So I see that for every 1 mole of hydrogen, there's 1 mole of zinc reacting. Then I need to convert this to grams of zinc. So I know that for every 1 mole of zinc, the GFM should be 65.4. And so that should tell me that my mass of zinc would be somewhere in the realm of 0.627 grams. All right, so in the next part of this, we're going to look at molecular effusion versus diffusion. So effusion is going to be the escape of gas molecules through a tiny hole into an evacuated space. where diffusion is the speed of one substance moving through space or through another substance. We're really more concerned with diffusion in this class, although sometimes we use the terms effusion and diffusion interchangeably. So this is our Maxwell-Boltzmann distribution that we looked at earlier in the unit. This Maxwell-Boltzmann distribution shows me that at any given temperature, gas molecules will have both high and low speeds. But as the temperature increases, the distribution of these speeds is found over a wider range. You'll have the majority of your molecules at higher temperatures having a faster speed, but I end up kind of spreading out this curve. As the temperature increases, you have a greater number of molecules that are traveling faster. And at the same temperature, particles with smaller mass will have higher average speeds than particles with larger mass. My particles that are smaller will tend to move a lot faster than my particles that are larger. And we can calculate the something called the root mean square speed of my substances, which I denote as a lowercase u RMS, which stands for root mean speed. Okay, so this is the root mean square speed. How I calculate this is it's the square root of 3 times my gas law constant times temperature over my molar mass. So if I wanted to calculate the root mean square speed of helium and nitrogen, okay, I would have to do these separately. So again, my root mean square speed, I'm denoting with this U RMS, and then I can put an extra subscript on here for the substance that I'm talking about. So this is helium, and this would be equal to the square root of 3 times, we look back at the equation, my R. So the R that I want to use here is my one that's in joules. So when I'm looking back at this gas law constant right here, I want to use the one that has joules in it. So that would be this 8.314 value that we haven't really looked at. One other thing we should note is this molar mass here. This has to be in kilograms per mole. So it's a little bit different from how we normally look at molar mass. We normally look at it in terms of grams per mole, but in these problems, we're going to look at it in terms of kilograms per mole. So I'll take 3 times my gas law constant, which in this case is going to be 8.314, times my temperature, which is 298. Again, it does still have to be in Kelvin because we're dealing with gases, and my temperature for gases is always in Kelvin, and then divided by the molar mass in kilograms per mole. So I know helium's molar mass is 4 grams per mole, which is the same thing as saying it's 0.004 kilograms per mole. So I plug this into my calculator, and my answer will come out in meters per second, and my answer should come out to 1363 meters per second. I'm going to do the same thing for my nitrogen. I'm going to remember that nitrogen is a diatomic molecule, right? So it doesn't just exist as nitrogen. It exists as this N2. That's going to be equal to 3 square root of 3 times 8.314 times 298 over, I know that the GFM of that N2 is 28 grams per mole, but again, I need this in kilograms per mole, so that's going to be over this 0.028. Plug that into my calculator, and that should show me that this is 515 meters per second. And if I'm comparing these two values between helium and nitrogen, helium is much lighter in terms of its mass than nitrogen, and its root mean square speed is much, much faster. This shows me that heavier molecules tend to move slower, and lighter molecules tend to move faster. So the last part of this, we're going to be looking at Graham's law of diffusion, which means I'm going to compare the rate at which a substance will diffuse or effuse as compared to its molar mass. As we just saw with the root mean square speed, my heavier molecules should move slower, and my lighter molecules should move faster, which means that my lighter molecules will have a faster rate of effusion, and my heavier molecules will have a slower rate of effusion. So if we're looking here, the rate of gas A over the rate of gas B is going to be equal to the square root of the molar mass of gas B over the molar mass of gas A. So let's look at this in terms of an application here. So in this practice number 2, it says, what is the effusion rate for helium and nitrogen, and what does it mean? So I'm going to be looking at my rate. Oh, sorry, again, I don't know why it's doing that. Just erase that so it's a little bit easier to see. So I'm going to be looking at my rate of effusion. Oh. For helium over my rate of diffusion for nitrogen. And that's going to be equal to, if helium's on the top of my rate fraction, I'm going to put helium on the bottom on this fraction over here. So it's the square root of the molar mass of A on the bottom and the molar mass of B on the top. And these are the same molar masses that I calculated in the last problem, except now we're going back to grams per mole. So this rate is going to be equal to, when I solve this, it's 5.29 over 2 if I solve those square roots individually, which comes out to 2.64 over 1. That would be the rate comparing the two, and using Graham's law of diffusion here. What this means is that helium effuses at a rate 2.64 times faster than nitrogen. And this makes sense because helium is my lighter molecule here, so it should effuse much, much faster than the nitrogen. Okay, so go ahead and try it for this practice problem number 2. All right, so let's take a look here. Okay, so in this problem, I'm comparing the rate of hydrogen to an unknown gas. Okay, so if I know the rate of hydrogen over the rate of this unknown, I'm just going to call it gas X here, is going to be equal to, again, if hydrogen's on the top of the first fraction, the square root goes on the bottom of that fraction, so I know that's the square root of 2. And then on top is going to be the square root of my unknown molar mass. That's what I'm trying to solve for, is this unknown molar mass. Okay, so I know in the problem it tells me that this rate is 9 times faster for hydrogen. So that means that my rate is equal to this 9 over 1, which again is equal to the square root of x over the square root of 2. You see how I'm getting this here? Okay, so what I'm going to do now is I have to square my problems here. To get rid of this square root for my x, I have to square these problems, square this whole problem here. So I'm going to square everything. Okay, so when I square my 9, I end up finding 81 here. Square of 1 is still 1. Okay, square of my square root of x is x. And the square of the square root of 2 is 2. And now I should be able to algebraically solve this problem here. So I should see that x is equal to 2 times 81, which should give me 162. And that's grams per mole. And that would be the answer to this question. The molar mass of the unknown is 162 grams per mole. Okay, so now we have some practice problems in here, some review questions that combine all of our gas laws in here. That's what you're going to be working on for the remainder of this class today. So this goes through page 27. Okay, so there are 16 questions here, all multiple choice that I'd like you to try.